Hello, Srinivas sir.
Hello.
Sir.
Hello, you are able to hear me?
Yes, sir. It's clear, sir.
Yeah, fine. Very good.
Within 2 minutes, we will start the session, sir.
Okay.
Okay, sir. Thank you, sir. Good afternoon to one and all. It's my privilege to introduce Dr. T. Srinivas Garu. Sir has working on associate professor in Department of Electrical Communications, IISc, Bangalore. Sir, research interesting areas, sir. Photonics, fiber optics, optical networks, biosensor, microwave photonics. Sir has published more than 30 plus journals, international journals, and Sir has undertaken the projects. 5 government sponsored projects has been undertaken by Srinivas Garu, and Sir has membership of professional in IEEE, SPIE, OSA, SIM, SIAM, IETE, ISOI, ISSS. So it's my pleasure to invite you, sir. Sir, Srinivas, sir, please hand over the session, sir.
Yeah, thank you very much. Let me start. Let me see whether I'm able to share the document. Then we'll proceed. Just a minute, please. Hello. You are
Sir.
able to see the slides?
Yes, sir.
Let me
It's
make it
clear,
full
sir.
screen. Yeah, just a minute. Let me make it full screen. So, good morning. I hope you are having a very interesting workshop. I have seen your schedule, and I hope you had already got some idea about quantum information. Okay, so my topic is on quantum communication and computing using photonics. Basically, we'll deal with quantum information, okay, whether you use it for communication or computing. So, but the main idea here in this talk is to use optical techniques to implement optical communication and quantum communication and quantum computing functions. This is one of the recent areas of interest in our lab. And of course, as you know, the quantum is a very big buzzword now. Everyone is interested in that. But of course, a lot of loose ends. There are many things that we need to clearly understand. That's an important part of learning this quantum communication and quantum computing. I hope some of you are already learning something, already have attended some seminars and you have learned something. And I hope this lecture will be useful to you. So I was given a lot of time, about 3 hours is there. So in the first part, I will talk about some basic things, how photonics can be used. And in the second part, I will deal a little bit with photonic integrated circuits and a little bit of work that we are doing in our lab. So this is a brief outline of my presentation. We'll start with the role of photonics in quantum communication and computing. Then we'll take up some examples and then see how you can implement optically. And then we'll deal with devices, photonic chips, optical chips on the substrate. And then there's a new idea of what is called this few mode communications that people are doing to enhance the bandwidth in traditional communication systems, traditional optical communication systems. Then you can extend it to quantum communications. People are talking about higher dimensional operations like multi-level communications. People are talking about higher dimensional quantum communications. And a lot of in between on the chip computing also a lot of people are trying to do. In particular, there are a lot of logic gates, etc., that are being implemented by using the optical techniques. So the crux of the problem is, if you want to implement quantum information functions, optical techniques are the best way. And photonics is a broad name that is given to all these technologies. So the first slide, we'll try to spend some time on what is photonics and how optical devices play an important role in present day applications. I hope some of you are interested in this subject. Photonics has got a role to be played in many applications, starting from optical communications to optical sensors, then optical computing people are talking about, and now people foresee that photonics will play an important role in quantum communications and computing also. Quantum information technology, that is a word that we can use loosely for all these things that we are talking about. So you can please ask some questions in between if necessary. You can pass them on to the organizers on the chat box and they can interrupt me at any time, and then we can have some discussion also, because a lot of time is there and I don't know whether I'll be able to use all the time. Okay, so photonics can be said to be the science and technology of using light wave particles for any applications. This can be said to be analogous to electronics. As you know, in electronics, you use electrons, which are the fundamental particles, and all the devices that correspond to that. So you have a lot of electronic devices like transistors, then diodes, up to ICs. All the applications that we see now, like the cell phones, the laptops, and the TV, are all electronic devices. So our IT industry is based on electronics. But of course, there is an important development in about 1960s, you can say, the fiber optics. So fiber optics is a technology where light is used for transmission of information rather than electrical signals. So that has revolutionized our communication scenario and got all the broadband and all those things. That's an important development. We can say that photonics will play an important role. And quantum is an area where photonics will play the most important role. We can hope that photonics will play the most important role, because if you see the quantum world, a lot of theories are available already, a lot of algorithms, a lot of techniques, and so on and so forth. A lot of theories already developed, but there is very few ways to implement all these theoretical proposals. So we can say photonics will play the role. So what are the properties of photons that will be useful in all these applications? We should look at quantum nature of photons. Light is an important object which has to be understood from quantum mechanical point of view, quantum physical point of view. We can say quantum physics, not necessarily quantum mechanics. As you know, all these particles have quantum nature, not simply the classical nature. If you have a lot of big light, for example, from a light source, you can, for some applications, you can say that light propagates in straight lines and you can treat them as a classical waves. Whereas for many applications, like the lasers and now in this particular application, usage of single photons and so on, you will require quantum nature of the photons. So you can say that, like in electronics, you know, we use Fermi-Dirac statistics to study the properties of electron devices, where the electrons can occupy only certain levels and no two electrons can occupy the same level, and so on and so forth. These are the properties of Fermi-Dirac statistics. Similarly, we use Bose-Einstein statistics to study the fundamental properties of light and photons. So there are a lot of differences are there between electronics and photonics. You know, electrons have got certain mass and certain speed and certain charge, and all these are the properties of electrons. Similarly, you have the properties of photons. They have almost a zero rest mass, so they are very fast, and you can also manipulate them. And of course, it is difficult to manipulate. There are no charge on the photons, so it's difficult to manipulate, but they cannot interact with external world. That's an advantage. The EMI, EMC advantages are got by using that property of the photons. Similarly, there are a lot more properties of photons, which as we go along, we'll see. For example, the angular momentum of a photon is an important property. The spin of a photon is an important property. And as you know, there are several categories of fundamental particles, which include one of them is the photons. So in conventional electronics and communication engineering and computing, these are all signals are the ones we operate with. You can generate signals in the form of light. You can transmit light from one point. These are all the operations that we do in electronics. The same thing can be done in optics, in photonics. So you can transmit optical information from one point to the other. You can control the light. You can do a lot of optical signal processing. You can display information, images, and so on. All this can be done with light also, like electronics. Except, of course, I have put storage is an important problem in photonics. There are different ways to approach. Of course, I'm not saying they are exactly equivalent, but storage is an important problem, and there are different ways to handle that. So there are a lot of things to come. If you see globally what is happening in the world of photonics, you see that there are a lot of technological developments in the lasers, in the applications, in the biomedical world, and so on and so forth. So we can say that photonics is an important technology in this world. Similarly, there's a lot of academic activity. Many universities have got programs on optics. At least in India, you know that we have fiber optic communication courses in all colleges. And there are certain faculty members and scientists who are working on applications of photonics. They have some projects are there. Government of India is also supporting photonics very much. We also have, national initiative on photonics. So they have some plans of introducing fiber optics everywhere. National network, you have. Similarly, national initiatives are there in other countries like European countries, American countries, and so on. So photonics is a technology to reckon with. We cannot ignore. In fact, if the placement scenarios and other opportunities improve, we need to introduce BTech degrees and so on in photonics. So this, of course, this is not a lecture on photonics. So I will not spend too much time on these things right now. Maybe in the second part of the lecture, I'll tell you a little bit about photonic ICs, which will be useful to study the quantum properties and quantum information properties. So we'll start with quantum applications. I think you must have had an introduction in the beginning yesterday and today on what are qubits. Let me go to the next slide. Of course, because this is a new subject, we have been giving our own perspective of quantum information. Okay, the most fundamental thing, that first thing that we encounter in quantum information technology is the representation of information. So you start with the qubits. Just a minute, please. We'll go back and then back and forth, or maybe let me continue with whatever is there in the slides. So you know that you will use the quantum nature of objects to represent information. In quantum information technology or quantum information theory, you use quantum nature of the objects to represent, not classical in nature. For example, in electronics, you use current levels or voltage levels. 0 represents certain current level, 1 represent another current level, say milliamperes or something like that. Or you can also say light intensity can be used. So much of 0 milliwatts will represent 0 bit and 1 milliwatt represents 1 bit, and it is very deterministic. You can also use the polarization state of the photon. I'm just taking examples. Of course, sometimes we observe that, of course, maybe at the end I will make a comment that at the moment, other technologies that are used for quantum information technology include atomic systems, nuclear systems, and so on. So all these are somewhat more sophisticated and complex technologies. You require very low temperatures or more sophisticated mechanisms to maintain and create these systems. It's not very easy to create a single electron, isolate a single electron, or manipulate the atomic levels of an atom, and so on and so forth. The same problem arises with light also, but it appears to be better than other systems. So I can say that optical methods are very good for quantum applications. So you can use the spin of an electron as an example. Polarization or angular momentum of a photon can be used. And in the more extreme sense, you can use gravitational waves. For example, if you are getting some communication from extraterrestrial objects, you can expect that, just a minute, please. You can expect there are a lot of atomic or quantum phenomena happening in the extraterrestrial world. I hope many of you have thought about that most of the phenomena that we are encountering on the Earth or nearby Earth, the solar system or so on, are somewhat not so quantum or relativistic in nature. We can understand them by using classical methods of physics. Whereas the real world, we can say, is really a quantum and relativistic world, and all the laws of physics, etc., will not work once we cross a certain system, our solar system or Milky Way. If you cross, we cannot expect the same physics to happen. And one of the important universal things that we know of is gravitation. So gravitational waves, I hope, are being used to communicate, not by living world outside this system, but naturally gravitational waves are carrying information about the extraterrestrial objects, which we can. So in that sense, we need quantum communications to understand many phenomena in the world. And of course, we can just simply compare a typical optical communication, quantum optical communication link along in a similar manner as that of a conventional communication link, except that each of these have to be defined properly. So you know that you need a source of qubits or photons, single photons. As you know, we have to manipulate single photons, pairs of photons, and so on. So you need to have a source of information, source of physical objects, and also a method to modulate this source. You have to impress your information that you want to transmit or manipulate on the source. Then, of course, we need to have detector very fine. As you know, all these properties are very small. The power levels contained in the photon are very small, so you need to have detectors which are very sensitive. Sometimes the noise is going to be an important problem, and we cannot overcome that. Similarly, the channels, the free space channel, the fiber optic channel, these are all some of the channels which can be used for quantum communications. These also have to be studied separately. So we need a lot of mathematical techniques. You must have already come across now when you are studying in the beginning, in the introduction, you must have come across a lot of mathematical techniques to represent the information, to manipulate information, and so on. So a lot of mathematical techniques are needed. In particular, the quantum mechanical techniques of solving the, I think in the next slide I will go. So we need to understand how quantum states of the objects are used. So you know that the properties of the objects are not clearly defined. If you have an electron, for example, you know it's, of course, the electron is also difficult, but let us say the conventional object, say current level, you know exactly. Okay, so if you are using bits in the classical thing, you know that you have 0 level and 1 level, which are well defined and are represented by currents or voltage levels, and these are well defined. Whereas the quantum objects which are used in the quantum information technology are not well defined. That means there are probabilities associated with the states. And so quantum mechanically, you require wave functions to study these properties. So these wave functions are nothing but the probability distributions of the object states. And so the measurements or the observations are defined in terms of the averages. You know, if there is a PDF of a particular state, you can define, say, for example, the position of the object by its average or expectation, and also higher moments, sigma and standard deviation, etc., are used to study the properties of these PDFs. So the observations or the measurements are defined in terms of the operations on these PDFs. That is an important difference in the operations between the classical and the quantum world. In the classical world, you use exact calculations, either linear algebra or differential equations, to exactly specify the values of the states or values of the objects like current levels or voltage levels. Similarly, quantum operators, not simply the exact values, use the operators to define operators who are operating on the wave functions to define the measurements. So the position of an object is defined as an operation, expectation operation on the wave function. So we will not delve too much into mathematics of this, but let us try to understand the basic idea. I hope I am clear. In the classical world, we use exact values. In the quantum world, we use operators and averages. So the first thing that, as I said earlier, the first thing that we'll encounter in quantum world is the quantum information. What is meant by quantum information is an important issue that we are trying to discuss right now. So I said just now that there are different levels in a quantum object, like 0 ket and 1 ket are the averages of the PDF describing the zero state, maybe either energy or polarization or whatever, angular moment, whatever you like. And one is the level, distinguishable level. For example, always, even though it may not be exactly true, exactly analogous, let us use polarization of the photon in this discussion. In this lecture, let us use polarization photon to as a zero state and one state. So the polarization, maybe not this picture, you imagine a two-dimensional picture where maybe this itself without 3 dimensions on x-axis or the horizontal axis, you say the zero cut state, or I am putting in the z state, z direction, and on the vertical axis it is one state. Okay, this is average. So probability that for this state, there's a probability that photon is in this state. So that probability is described by this alpha and beta. It's a superposition of these two states. That means a given object can remain in a superposition of these two states. And so once again, because it's a combination of two PDFs, there's also the average state and so on. Physically, if you are confused, you can use the vector notation and you can say the angles represented, angle from a certain axis, angle from zero axis as the qubit state. So the qubit state can be is not well defined, it can be defined by a probability distribution function. So this is the average of the psi, average of the property of the photon that you are talking about. So you know that you must have already come across alpha and beta are the complex numbers, and the square of alpha square plus beta square is 1 because the total probability of the photon being in a given state is 1. Okay. So you must have already seen in the previous, I think you must have come across the previous lectures that you represent the qubit states on a Bloch sphere, and there are infinite number of possible states for the qubit, for the photon, you can say. So this is also extended to multi-qubit systems. You know, you represent, there are two, that means you have two objects. Let us assume there are two photons representing the two qubit system. Each can independently uncorrelated. Let us assume for the time being, let them not be correlated. I'm not using the correct word. Let them not be correlated. You can talk about first photon being in a 0 ket state and second photon is 1 ket state, and you can think of all the combinations. So you have a basis consisting of 0 0 ket, 0 1 ket, 1 0 ket, and 1 1 ket. So there are 4 basis vectors to represent a 2 qubit object. The psi represents 2 qubit object. The PDF of this is given by a combination of all these with 4 coefficients. That is in a 4-dimensional space. So 4-dimensional space. Suppose if I am using conventional terminology, if I have n qubit system, you have n qubit system, you can have 2 power n basis vectors, and so you can say that there are exponential order of classical bits to map this n qubit system. So there will be more theoretical calculations. If you look at the standard textbooks or journal papers, you will know you can calculate, you can estimate the information content into. Of course, I'm just assuming that we are talking about the information in the classical sense, but if it is a quantum information, there's no comparison between the classical n qubit system, n bit system, and n qubit system. And similarly, all the mathematics changes. For example, the entropy of an n qubit system, instead of Shannon theory, you have to use von Neumann entropy. And of course, mathematically, it has got a lot of ways to represent. Then, of course, I will just go to, this is a summary of comparison between the classical and quantum information in terms of the states representation, in terms of the what to use for the computational primitives, in terms of transfer operations, gates. What I mean is gates, and then speeds of operation. There are a lot of things which don't have a comparison with classical things. That's what is, this table is from the standard, one of the standard papers by Bennett and Shore on quantum information. Anyone who is interested should have that paper. Of course, a lot of other issues. I am not going to highlight them. The noise properties, then the various error correction techniques, and so on and so forth. Whenever I have a suggestion for those who are trying to understand. First of all, I would suggest you go through a classical way, something which is there in the classical, what it happens in the quantum. And next step is mathematically. You try to replace the deterministic objects with a probability distribution functions and in that notation. So then, of course, we have to understand what is the relationship, but way to represent and understand these quantum information technological mathematics. So I'll look at a few logic gates and how they are implemented using quantum information functions in using photonics. So there are, as you know, there are a lot of gates in digital logic. As you know, the whole world is now, all the communications computing is based on the digital operations, and logic gates are one of the important things. You can simply think of these logic gates as a transfer matrix operations. You have an input function, input vector, you have an output vector, and there's a matrix relating input and output vectors, and this matrix will determine what is this gate operation. For example, if you have a matrix 0, 1, 1, 0, it will represent a NOT gate, and there's a special one, Hadamard gate. I think someone must have told you already. It's a superposition state where, if you have, I will show you a picture in a minute. And similarly, there's a controlled NOT gate. There's an extra one more port resulting in 4x4 matrix. I think I'll show you in a picture in a minute. So, for example, there's this Hadamard gate. You can observe the input vector is transferred on a superposition vector. So we don't know what is the state of the input qubit. So if there are 0 and 1 states, the output of Hadamard gate is a superposition of these two. So these are matrix 1, 1, 1 minus 1 is the matrix representation for the Hadamard gate. So one of the important applications of the quantum, which is demanded in the real world, is called the key distribution. Highly secure communication is important outcome, you can say, of quantum information theory. This is a technique to share secret keys between two users. See, one of the important reasons why this has become important is we don't know the actual states of the objects we are using. So how do we operate if you don't know the states of the objects that we are talking about? Suppose you don't know whether it is 0 or 1. In the classical sense, suppose you don't know whether the information is 0 or 1. How do you operate that? It's an important problem, you can say. And there are a lot of techniques, a lot of protocols have come out to use them. So these are called the QKD protocols. You have come across, I suppose, maybe, I don't know whether someone is reading some of these already existing literature, or this is the first time that you are encountering this. I will suppose those who are interested in this subject have already browsed through the web or Wikipedia or some YouTube videos, so that I will assume that some of you are familiar, or if I mention also, you will be able to understand easily. So BB84 is one of the important protocols which has been announced long ago, in about 1984 in India. Then these are some of the E91, E92 or more recent protocols. So the main problem in this is to transfer some qubits from one point to the other, and without looking at them, because we don't know what are the states and how do you operate on those. That's an important problem. I'll try to use optical techniques to illustrate what is one of these protocols. I would like to ask Mrs. Bhavya whether BB84 protocol is discussed earlier in the previous lectures. Hello? 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 Any of the organizers listening? Or any of the participants can speak out whether BB84 protocol is discussed earlier?
Yes, sir, it's audible, sir.
Hello? Is it audible?
Yes, sir, audible, sir.
So I whether BB84 protocol was discussed earlier in any of the lectures.
No, sir.
No, sir.
Is that so? That's one of the most important these things in quantum information. Right? Anyway, I'll try to show you a little bit. Okay. Okay, let us get going. So I will use BB84 protocol to illustrate how photonics or optical techniques are used for QKD. Okay. So this is one of the earliest protocol and is based on polarized photons. As you know, the photon has got polarization is important property of the photon. So there is a source of information like not exactly a light bulb, a single photon source, and there's a detector at the other end. So traditionally in quantum communications and computing, people call Alice as the transmitter, Bob as the receiver, and Eve as the eavesdropper in between. I'm not showing that one here. So let us assume there's a transmitter, there's a receiver, and we have to transmit quantum information securely. So what is how do we do that is an important question. So Alice has got two options. So you know that quantum information, the photon, if this thing is representing a photon, it can be represented as a superposition of zero state and one state defined as horizontal polarization of the photon and vertical polarization of the photon. Okay. 0 ket plus 1 ket superposition will give you the psi ket. Similarly, I can also say that the same photon state can be represented by a left circularly polarized photon and right circularly polarized photon. So let me say 0 dash and 1 dash for these two. So alpha into 0 ket, beta into 1 ket, superposition. And alpha dash into 0 dash ket and beta dash into 1 dash ket is the second one. There are two different ways to represent the given photon. Let me say these are two machines. Let me say Alice has got two machines. One machine will give you horizontally polarized photon and one machine will give you vertically polarized photon. Whether this 0 comes out or 1 comes out, you cannot say it is chosen randomly by Alice. That's an important point in the protocol. Similarly, Alice has got the option to choose the second basis, left circularly polarized and right circularly polarized. For the same, for same incoming qubit, she can use left circularly polarized and right circularly polarized. So the actual state is psi ket alpha dash 0 ket plus beta dash 1 ket. So two different ways. Let us assume two machines. So which machine Alice chooses is a problem. So Alice will choose these machines randomly. So now you can work out what are the probabilities. Similarly, now let us keep that Alice aside, transmitter side. Let us go to the receiver side. So receiver side, the Bob has got two machines, like what Alice has got. One is horizontal vertical basis, one is diagonal, left and right diagonal basis. Almost identical to what Alice has got. And then when a photon is received, the Bob has a choice to choose the first basis or the second basis. See, the given photon state psi can be represented as a proportion of this or this. So Bob can choose randomly this basis. If you choose this basis, you will get a photon with 0 or 1 qubit according to the state of the photon. So only the choice of the basis is an important thing. So Bob also will, let us in this protocol, Bob also will choose the basis randomly. So depending on which basis he chooses, you get the output. So now I would like to calculate. So if one qubit is sent and Alice uses one of the first machine and Bob uses the second machine or first machine, what is the outcome and what is the probability? If another photon comes and Alice chooses next qubit, not bit, and Alice chooses one of the machines randomly and transmits, and Bob also chooses randomly and receives, what is the outcome? So we are not looking at Alice or Bob, we are not looking at what is the photon state, but only randomly they are choosing their basis or the machines. So here is the table. So all the combinations that are being shown here. So bit sequence, these are the bit sequences that that represents the qubits states, and these are the photon states. Suppose, for example, if one is the bit and Alice uses the second basis and the outcome is right circularly polarized photon, that is one, and this is the Bob states. So Bob chooses the first machine vertical, horizontal, vertical basis, and he receives a 0 according to this, and next bit is qubit is 1 chosen by vertical basis by the Alice, and first machine horizontal vertical basis by the Bob, and 1 is the outcome, and so on and so forth. So you can see what are the outcomes. So these are the input states, these are the output states, and you can calculate what are the probabilities. So if you want to look at the probabilities, you will see that this is not corrected properly, this is received properly, this is not received properly, and so on. So if you calculate the probabilities, you will see that the 50% of the time they don't match. So Alice and Bob will have to match their choices, whether they have chosen first basis or second basis, vertical, horizontal, or diagonal. They will compare because that is in their hands. It's very definitely they have chosen randomly. They have chosen randomly. Maybe let us, you can assume the traditional dice or coin tossing, with a coin tossing experiment, they can choose this and then decide. Of course, once they made the table, they should compare whatever they have done. So we can expect that 50% of the time the outcomes are correct and 50% of the time they are not correct. So if a sequence of qubits are sent, they have to take only, they have the table only when they have done this. So 50% of the time they are wrong. So this is an important test of this protocol. Suppose I disturb this setup. Suppose I say that I will use, say for example, this probability is not equal, just as an example. Then what happens? This probability is disturbed. It's not 50%. So you know how much percentage of the time they should be correct. So if there's any deviation from that, you can say that this is compromised. Okay, that is the idea behind the BB84 protocol. Just to give you a hint about the usage of this, suppose there is a eavesdropper in between, someone is trying to tap. So the Eve also has got similar idea. Say she knows that Alice and Bob are doing this and comparing with the BB84 protocol. So let me get also 2 machines, 4 machines, in fact, 2 for receiving, 2 for receiving and 2 for transmitting. And she does also the same thing. You have to repeat this twice. This argument, whatever I have mentioned, you have to repeat twice. And you will see that only 24% of the time, Alice and Bob idea will match. Whatever Alice and Bob says, they will observe that more than 75% of the time they will have to reject. That means someone has interpreted in between. So this is the crux of the BB84 protocol. Of course, this can be explained using other systems also, but it's very convenient to use photonics to explain this protocol. Similarly, the other protocols also people have tried to explain, and a lot of discussion is there in the literature about how this can be done. So this represents this picture or this protocol or this mechanism, what I've described, will clearly show the main difference between a classical key distribution technique and a quantum key distribution technique. I hope I'm somewhat clear, even though I have not done full calculations, but the crux of the problem, I hope I am able to describe. So let us go to more photonics. So that is just as an example I have given. I'll show you more pictures about how photonics is used in quantum communication and computing. So I have already described this story. Just now, in the beginning, in the first slide, I have told the importance of photonics and so on in the quantum world. So this shows some picture about integrated photonics. See, earlier we have used bulk optics, light propagating in uniform space from one point to the other. If you want to transmit information over a long distances, you have to use optical fibers. These are the correct way to transmit information. Now we are talking about computing. You can do it on the chip. If you have a silicon wafer or some other crystal 3-5 compound semiconductor chip, so there can happen a lot of logical operations can happen on the chip. So this is a topic where integrated photonics comes into picture. You can say integrated photonics or integrated optics is analogous to integrated electronics. So you know that VLSI is an important technology in the present day, and a lot of chips we have like memory chips, processor chips, and so on using VLSI technology. Similarly, you can say that you can make a lot of components necessary for an optical system on a small chip, and you can call it as integrated photonics. So it appears that integrated photonics is going to be very important for quantum technology. At this moment, you know that silicon is an important material. Because of VLSI, silicon is important. People have developed a lot of technologies on silicon. And not only silicon, little bit of silicon carbide, silicon nitrides, etc. are also used. This is an important system for integrated photonics. Similarly, people have thought about 3-5 materials. Importance of 3-5 materials is they are active materials. You have what is called this direct band gap to many of these materials, and you can make lasers. You cannot make lasers easily in silicon. There are recently some proposals on some ways to use silicon for lasers, but that is very difficult because of band gap characteristics. And 3-5 is very ideal for this application. And so people have thought about forming integrated photonics in 3-5. This in contrast to silicon. Silicon is very good. All your chips are based on silicon. Electronic devices are based on silicon. Whereas you need 3-5 materials for integrated photonics. And also, as you know, there are a lot of nonlinear optical effects are needed. For example, if you want to generate a single photon source, how do you do that? As you know, you have to use nonlinear optical effects to generate single photons. So these are traditionally lithium niobate, then some of the potassium, I don't know what is I forgot the name of the many crystals. So a lot of crystals have nonlinear optical properties. So nonlinear properties are needed, and traditionally crystals are already there for optical applications. They can be used for integrated photonics applications for quantum. Similarly, there are a lot of other new things that are coming up using, this is a technological part. When I said platform, it's a technology part. You need to have processing, fabrication, and so on and so forth, which are becoming more important. People are trying to hybridize. On the silicon itself, people are trying to formulate or fabricate extra materials on top of that and generate these properties, nonlinear properties, active properties, and so on. So they use various techniques like femtoconductor lighting, etc., to create these integrated photonic devices. So if someone who is interested can see the recent paper on this Journal of Optics, integrated quantum communications. So what are the various devices that you will come across? I'm trying to show you some devices for communications applications. So you generating, manipulating, and storing and detecting of quantum states is an objective. One important design element for all these devices is the operating wavelength. At what wavelength will you operate is an important question. As you know, optical communication uses 1550 to 1530 to 1560 nanometers as the window, optical communication window, and they use optical fibers. So people have tried to create quantum communication also using optical fibers at this communication wavelength. But of course, if you use free space as optical communication in a laboratory, if you want to set up a quantum communication link from this end of the room to that end of the room, more convenient one is a free space. Visible light also is very good. Or sometimes, depending on the sources that you have, you can create integrated devices. But of course, I'm not discussing too much about the free space communications, but on the chip. So this is an example of integrated quantum communication devices for generation and manipulation of photons. How do you generate and manipulate photons is an important question. This is a typical example from one of the recent papers, you can see. So you have a grating coupler. See, let me say this entire thing can be on the chip. See, Bragg reflector means a grating. This is a little bit a grating. There's a periodic variation of refractive index here, and it can reflect light or a photon. See, whatever I'm saying with the light, you can replace with photon, and it can be used for. So you have a grating coupler to couple the light into this, and there's a resonator. I'll show you more about the properties of the ring resonators. So in integrated optical devices or integrated photonic devices, one of the key elements is an optical waveguide. Optical waveguide is like an optical fiber. Maybe I will have to go back to one of my another slides to show what is integrated photonics. Maybe I'll try to do it later after some time. So this resonator is a device in which the light can rotate and it can resonate. It can be coupled from the output grating coupler to this waveguide and coupled to the resonator. And then this is the output port of this resonator. And you have a reflector, the Bragg reflector waveguide with periodic variation of the refractive index acts as a Bragg reflector. Of course, these are all the size, whatever you are saying, 2.5776 millimeters is the length of the Bragg reflector. It will reflect one particular wavelength. For example, lambda b of 1553 nanometers can be reflected depending on the design. And remaining two are transmitted. In this case, I will use it in the opposite sense, in the reverse. So you can call them as input ports, drop ports, and throughput ports of this coupler. There are 4 ports. This you can say that this waveguide is a bus waveguide. Light can pass through this, and it can couple into this ring resonator. And it can come out of this port. Depending on the resonance, you can drop the signal at this port. You can also drop the signal across these ports. Suppose you have 2 signals that are coming up, you can drop one across this port and one across the other port. So if you have a couple of photons to operate, you can use such an arrangement to separate them out. Let me say one is representing 0 state and one is representing 1 qubit state. Then you can measure the states at this. You can see what is the probability of 0 qubit state and what is the probability of 1 qubit state by using such an arrangement. So you only have to design this ring resonator properly. In this particular example, you see that ring resonator of 6.55 microns is dropping blue signal, and ring resonator of radius 6.5 micron is dropping the red signal. One can be seen, depending on the application, you can say one is the idler, one is the signal, and so on and so forth. Let us go to one more example. So this is also another example of a generation and manipulation of photons on a chip, but more sophisticated. You have a delay lines here. In this case, if you want to delay a particular signal to a certain extent, you can use these delay lines. It is only pictorial representation. In principle, in practice, it could be a loop of a fiber, for example. You are sending both the signals. There are 2 signals, pump signal and a source signal. In many applications, as I said earlier, you need nonlinear optical effects. To excite to invoke nonlinear optical effects, you need to have a higher pump level power. If you take a crystal like a lithium niobate, its nonlinear properties will be apparent when at a high power. So you use a pump at a higher power level to excite nonlinear optical properties. And along with the pump, you send the source, the information photons, which can be manipulated by this. And also you can also delay. In these 2, you can see that it may not be very apparent, both these signals are there here. Both the qubits are there in this loop, and they can pass through this set of devices. You can say these are interferometric devices. There's a chip A and chip B, and you can also communicate between the chip 1 and 2. And also there is a source of information which has got a loop of fiber and so on and so forth. So you also see that there are couplers. The waveguides are intersecting. There are couplers to exchange photons between them. Of course, you cannot divide the photon, but there's a probability that light is exchanged. The state of a photon in an interferometer, this is called an interferometer, can also be expressed as a superposition of the states. So you can analyze the state of the photon in a certain way. Even though we may not be able to say exactly what is the state, we can analyze what could be the state. So there are a lot of, these are all the mechanisms to manipulate the photons. First of all, you are generating using a loop, and then you are trying to manipulate using this circuit, this interferometer, the coupler, etc., etc. So this other, of course, this is not a fully manipulating, this generation of photons. So you have a system like a laser. You can say this is like a laser, except that it has to operate with a single photons. Only one photon has to be generated, the output. And of course, as you know, you need to have a nonlinear optical effect. So there are several layers in this. Typically in a, what is it called, your gallium arsenide or indium phosphide material system, you can have gallium arsenide and gallium arsenide and all the combinations to several multi-layer structure you can create, like in a laser. And then you can create and manipulate single photons. So this is a system. Earlier one was a system where you use passive optical effects. See, there is no, these are all not active materials. Like these are like, what is it called, lithium niobate or some crystals, which can have nonlinear effects, but dynamic but not active. You cannot generate photons directly in a lithium. You have to generate them outside, externally. In this particular case, this is an example where you can generate the photons, single photons on the chip. So this is an example, another example of a generation of single photon sources by using a periodically poled. So different states of the photons can be generated by using different mechanisms. You can have two different paths and so on and so forth to create different states that you would like to have. You can have a combination of states that can be generated. So this is also another, of course, this is using silicon photonics. This is a silicon chip for manipulation with very short, ultra short lasers. You can write these waveguides. See that he is highlighting in this particular paper, they are highlighting how these waveguides can be formed by using femtosecond lasers to write waveguides. So you can manipulate this photon. There is this close by. These two waveguides are close by, so you can light can exchange between them, and they can act as a conventional wave plates or beam splitters, etc. in conventional. So this is on silicon itself. There is no generation, or generation will be there outside. But if you use 3-5 material systems, you can do everything on the same chip. So this is a fully picture of a chip integrated on top of aluminum nitride waveguides, and so on and so forth. Of course, I don't know what is the, of course, they describe in this paper. If you go, you know how all these things that are described in this. This is a final, this is a chip, this is how it looks, a photonics chip for quantum communications. So this is another, this is not really a picture, but it is a schematic of QKD system. You can put entire thing on a single wafer. This is an experimental setup for QKD. So standard components, not very strange components here, like you have the waveguides, delay lines, sources, and some electronics is also needed. We cannot give up electronics because a lot of signal processing will be done by electronics in many systems. So many times if you see a quantum information system, there's a big, like the innate days of innate computer, they show a big setup for small few qubit operations. So this is a schematic of that. So these are further examples. You can also create micro lenses and so on the chip. You can also create the polarization devices, waveguide arrays. Also, you can put lenses. You can make all of them. You can make on a small chip. At this moment, you can make. I mean, passive devices can be easily be made on glass or silicon technology. So conventional optical elements like lenses, prisms, polarizers, lenses, etc., can be made on the same crystal system in this particular case. So there are more examples like this. Integrated quantum communication systems. This is a fully architecture consisting of several devices for discrete, variable, and distributed QKD protocols. Different types. As I said earlier, there are different protocols have come up. After BB84, a lot of improvements have been done. You can, given a particular protocol, you can think of what are the devices useful, what are the ratios in which you have to manipulate the light, and so on. You can come up with a platform or a system, slightly more general purpose QKD system can be thought about. So basically it uses interferometers, like what I mentioned in the previous slides also. It uses Mach-Zehnder interferometers and delay lines, other than the sources which are there outside. Of course, you can also make use of all the components that are available for optical communications, like the amplifiers and then routers and so on. Of course, in particular, I would like to mention that you can make a multi-user system on the same chip. We have always been talking about point-to-point communication. So it is also possible to communicate among many users, not in the distributed space or also on the chip. So I think tomorrow's we will have a lecture on quantum internet or quantum networking, where there's an important problem of distribution of quantum information across many users. That's an important problem. That also people have thought about using on the chip devices. You can make 3 or 4 points, nodes, like what we do in networking. You can create nodes with some properties, some devices, so that quantum information can be exchanged between these two and manipulated by more than 2 users. That's an important thing that is we can expect in the near future. That's an interesting application or development. So sometimes packaging, of course, is an important issue. Any system, if you have to be used in practice or in the field, you have to package it well. And these are all the practical problems that you will encounter. For those who are trying to build systems, in fact, there are a lot of projects that are coming up to set up 4-qubit system, 8-qubit system, etc. And also computers, quantum computers, where you can manipulate. So you will have to package properly. That's going to be an important problem. So I would like to jump to some other thing. So of course, I'm not touching entangled states. That is an interesting problem, and I hope you have come across or you will learn in this lecture. So you can also manipulate entangled photons, like what we are doing with single photons on a chip. That's what I can make a statement. So these are practical QKD networks that you will have seen. Most of them use photons. So these are different examples. This is how the hype on quantum has grown. Now I would like to spend some time on multi-qubit systems or multi-level communications. In classical communications, you have many level communications like BPSK, QPSK, etc. We routinely use in digital communications. So you can use more than one levels, not only 0 level and 1 level, level 1, 2, 4, etc. communications, and you can improve the efficiency of communications. You can also optimize on the power levels, and all these things are the advantages of multi. Here I would like a few mode communication system. First, look at traditional set. Then we'll see how it translates into a quantum. Few mode communications is more than one mode of an optical fiber. In optical fiber communication, many of you know that we use a single mode optical. Only one mode is supported by the optical fiber from the other point. This is because if you have multi-modes, you have a problem, and it's very difficult to retrieve the information and so on and so forth. A lot are there due to dispersion. Of course, there are a lot of other problems in communications, like loss in the attenuation signal. Then many things are interrelated, like crosstalk and so on will come through. So we use single mode communication in optical communication. And there's an advantage of using few mode. You can design an optical fiber with 2 or more number of modes, 4 modes, 8 modes, etc. And each mode can be manipulated or each mode can be tackled separately, then you can transmit large amount of information. Many of you are aware about what is called this WDM, wavelength division multiplexing. In contrast to TDM and FDM, WDM uses many wavelengths. There are 4 wavelengths. Let me see whether there is a picture. Yes, let us use this picture to describe. This is a typical few mode communication system where you will need a fiber. This is this portion is the fiber with few modes. Let me say 4 modes can be supported there. You know, the modes of an optical fiber can be calculated or derived from the wave equation, and you can designate them LP01, LP02, LP11, LP112, etc. So these are the designations given to the modes of an optical fiber. Each has got a different propagation constant, each have got a different mode field, and also they have an important property of orthogonality. There is no exchange of information between the modes unless there is a perturbation. So if you launch second mode will remain. If you launch third mode will remain, and so on. If you launch 4 modes into this few mode optical fiber, 4 modes propagate without interaction. And each of the fibers can be modulated, each of the modes can be modulated separately. And so you have a multimodal communication. Suppose 10 Gbps is the data rate that you are transmitting. You have 40 Gbps if you have 4 mode system. In principle, I'm not going into finer detail, but you can enhance, you can multiply the capacity of the optical fiber by using few mode communications. But as you know, the traditional communication system uses a single mode. The fundamental mode is used. So you have of course, we want to optimize the laser power because laser is a costly device. You want to use the same device and divide it across all the channels. Mode 1, this is channel 1 with modulator 1 and data 1. Channel 2 with modulator 2 and data 2. Channel 3 with this N mode system, modulator N and information N. So there are N inputs. So a single laser diode can be used to split the power across all these things, and then you have to convert this. See, initially all this will be in the single mode, fundamental mode. This is the first mode, this is the first mode, this is the second mode, etc. But you have to translate this information into the first mode, this information into the second mode, third one into the third mode, nth one into the nth mode. So you have this mode converter is needed to convert modes from the fundamental mode to the whatever mode you want. This is a mixer, mode multiplexer you can call it. And at this point, if you see, there are 4 modes or 8 modes, each independently modulated and existing on those particular modes. So this is what is called the few mode communication systems compared to single mode communication systems. You have to do inverse operations at the receiver end. You must have a mode demultiplexer to separate out these modes from the fiber. Then you can convert back into the first fundamental mode and then use photodetectors to detect. This is how a few mode communication is done. And a lot of papers are there, a lot of information is there on the literature about what are the advantages, what is the channel capacities and all these things. So this is an example of a spectral efficiency. So still it is traditional only, not quantum. So we would like to make these quantum. See, one of the ideas in our lab and in this discussion is, I would like to convert this few mode into few quantum states. First mode I will represent by using the first quantum state, second mode by the second quantum state, third mode by the third quantum state, and so on and so forth. That is the idea in describing you this few mode optical communications. Okay, so this is a traditional few mode optical communication system with the number of modes 1, 2, 3 up to 1,000 modes. If you go, what is the efficiency and so on and so forth. So you know that there is a increase in spectral efficiency at the cost of other impairments. Let us assume there are no non-linearities or various other crosstalks and all those things. So you can increase the capacity of an optical fiber several fold by using this multimodal communications. So now you need the devices to manipulate these. Okay. So you need to have some mux demuxes, mode converters, and so on and so forth. That's what is given in this slide. You can use traditional devices like interferometers, directional couplers, power dividers, and so on and so forth too. You can create them on the chip. Maybe I think at this moment I will go on to another set of slides. Maybe I'll show one slide first, then we'll discuss more details in the next set of slides. So these are some traditional integrated optical devices. This is a directional coupler. It has 2 input ports and 2 output ports. These are all the top views. What you are seeing, this is a top view of a directional coupler. There are 4 ports, 2 input ports and 2 output ports. You can exchange between these ports. Okay. So let me immediately explain you the quantum counterpart of this. So single photons, if they are launched into the ports of this directional, then what happens? Traditionally, in the conventional sense, you would say that the power is exchanged between these. So 50% of the power can exchange from this to this. But in the quantum world, you cannot divide the photon. So you can say that the state of a photon at this point is a superposition of the states of the photon which could exist in this wavelength or in this wavelength. This is a truly good example of a superposition of states. And of course, it can also, because there are 2 input ports and 2 output ports, you can say that this device will manipulate. Just a minute, please. I'll close it. So similarly, branching waveguide. This is a branching waveguide or a combining waveguide. You can combine or 2 lights using this. You can launch this port, and you can combine. So later on, I'll show you in a minute that such devices can do quantum operations also. This is another device called the photonic crystal device. In the beginning, maybe this one you can see, this is a ring resonator. The waveguide in the form of a ring. You can launch the photons through this and then observe output. 2-bus waveguide here in this case. You have photon ring resonator. Crystals I have described. You can say photonic crystals are periodics. You can manipulate. These are analogous electronic crystals. In that ions are period arranged and you have valence bands and conduction bands due to that. Similarly, photonic crystal, you have stop band, pass bands. Light can pass if it is in a particular configuration, like blocked, some other configurations. Light can also photonic crystal ring resonators. These are examples. So just as an example, I'm Hadamard gate implementation using optical tube presenting T0 by T by T1 in this wave. So at a point, and if the input port, you can say that photon is position of T01 and T1 port. And in the case of fiber, they are independent. They cannot. In the fiber, they can be. So if you launch a single photon in this port, what happens is a question. So it can get state or state. The branch will divide, whereas it cannot divide. Photon can go through this port. This port contain 0 get states and 1 also in this state, and this can be said to be the 0 get. So that this is, of course, each of them with probability. So the outputs are equal to Hadamard gate operation. The same thing can be implemented on the crystal circuits. I have waveguides, some very small value of this will represent cases where they will have the mid and opposite and outside. So holes in a silicon wafer, I take mask it and holes lithographically that will represent a photonic band gap and using lithographic photonic band Y branch. So if you want to use BB84 protocol, what will you do? One question, you can create photonic crystals like this, source A and single photon source B, source A and single photon source B. Listen, you that we need different setups. Verticalization, one for lateral polarization, right circular. Let's go. So you have the input information, We have the one it's combined using a ring resonator, and of course here this chip is separate, Bob is separate. Detectors also are made on the chip, and you have an output data. In case you have Eve which has to stop this uh, system, this is I have not there at that point, but here you can see that Eve also has got to detect the from the tapping from the ellipse, and then she will use whatever is received Bob's side by transmit. See the information once again quantum information. So as I said here, when these and Bob their choice vectors and the outputs, they will find that there is only 25 match. That means you has opt. So this is how you can think of, and what are devices we calculate this we have here on the sense, and I can show you once again. So now this is a to implement on the photonic. Implement quantum computers. What do you do is an important question. Called HDKD is encoding discrete quantum information, higher dimensional code was that instead of use more and have to use more number of modes basically, and instead of qubits, they call it qubits. Qubits are used dimensional qubits. I say that qubits are generalized to d dimensions modes or d. You can say implement qubits. The same photon can be in different states. You can express the states of the photon in terms of multiple per photon. You can encode the information in terms of multiple bits. So this I already described it. If you want to use HD call with BB, instead of having two options, you should have so many basis options. You should D basis to represent. So Alice will make a random choice of the basis, encodes the information, transmits via whatever fiber or quantum channel. Then the Bob receiver performs a measurement on the random the keyword in also. After transmission, both compare the base over classical communication channel. They will and then compare. And if there is an eavesdropper, then the probabilities will be different. The measurement results will not agree. That is the so in the case of HD QKD, HDBB84 protocol, you need to have D basis. That is the most important conclusion. So implement that many sources SD. These are different. They are all combined single resonator and over this. The Bob also has got so many detectors and so on. All this can be made if someone wants to demonstrate or implement. You can make on single wafer, not silicon, but you have some where you can maybe let us say high system for that. So that's all I would like to say in this first part of the lecture. I hope I have described how used in quantum communications and computing. So a few examples used. Subject is still evolving. As in the beginning, the theory has already developed, and find when implement all these by using photonics. That's what at this moment. This lecture I will take one or more to illustrate how etc. computing in photonics to some of our work that we have done in lab. Thank you very much for listening. If you have some questions, any questions, please? Hello.
Sir,
Please.
decoherence problem is very computing.
Yeah, that's the problem. See, state of an object, like a photon, all physical objects. Is it not? In theory, think of where there is difference is not there, but in physical world there is a decoherence. If you have a certain state of a photon, it after some time it will not remain. Very short time, in fact. Most of the decoherence times are not very long compared to. So we have to manipulate. You have to create this which will handle along with the decoherence. So problem. Photon state changes. That is in. Yes, please. You have some more questions? So I will send a couple of papers for you to read through and learn more. Okay. So we will meet after another 15 minutes to tackle some more topics in photonics.
Okay, sir. Thank you, sir.
Yeah. We can join that at 3:30 or what is it? When do we start that?
We can join 3:30, sir.
Okay.
Thank you, sir.
Fine.
Hello.
Hello. Shall we
Hello,
start?
sir. Yes, sir. Sure, sir.
So I hope most of you have come back. So let us restart our discussion from where we left. So the previous lecture can be said to be just a very basic, or not exactly very basic, but more implementation oriented. Suppose you have some quantum information function, how do you implement using photonics? So it appears to be one of the important possibilities. There are a lot of difficulties will be there, I know, but I hope you will accept to a certain extent that photonics is a good way to implement. Okay. Now, in this part of the talk, I will touch upon one of our recent work done by some of my students to implement more sophisticated, more complicated function which we take up in computer science and engineering. Okay. Let me first share this. I'll share the paper first. I'm not going to show you, I've not converted that paper into slides, but I will try to show you the paper and then I will discuss a little bit. And then I'll show you some devices which I don't know where that. I hope most of you are able to see. Miss Bhavya, you are able to see this.
Yes, sir.
This is the paper I will discuss a little bit. Of our student, Shankar has worked on applying these photonics techniques to a consciousness problem. With see nowadays the machine learning and some of these artificial techniques are very very popular. He has photon networks to be applied to quantum neural networks. Neural, you need not worry these neural. I think when some of you are familiar, but you need not worry these neural networks and all those things. I'll illustrate in points. So you can see that neural network is a complicated or a complex system function. A lot of inputs are given. You have to process these and come to some conclusion. Important property of neural network feedback. Into cells, and in each layer there is an interconnection and a feedback and so on, resulting or conclusive output. And then of networks is process. So it's possible to do in linear fashion, one after the other. It takes enormous amount of time to see. I think many of these neural network architecture, typical neural architecture. There are layers I'm showing you, and at each layer there is computation going on, and in a linear, it is enormous. It's a very evaluation of some matrix. I give you many matrices and ask you to multiply. Number is very large. It takes of time. So if you simplify that by giving feedback and taking some conclusions and so on, it is very. So learning has to be done. It's a sort of training network to act and come to conclusion very quickly. That's what is meant by feedback and learning artificial new all these are artificial. Natural neural networks trying to imitate processes that go on in the brain, implement and algorithmics and architectures using that. Know about how these networks can be implemented, and each of these nodes, their weightage. You can see in the network parlance or from a graph point of view. you can assume each is known to certain with weightages. Basically, you simply using weights. So linear and then weight. And as you know, in quantum world, we represent matrices, density matrices. The quantum states can be represented density matrices. You basically have to implement the equation. Suppose if the functionality or the computation presented, how do you translate into a neural network, and how to translate neural network optical architecture is an important problem. What is described in paper. I will describe you a little bit. I'll see this paper also. But before that, I will show you a little. These are all the various things that he's done in his paper. He has converted the neural network, quantum meta layers, etc. I may not be, because this is something different thing, research, not be able to appreciate very quickly. But I hope after reading of the, you will be appreciate. This is what I would like to describe in this lecture. Go towards that. I would like give you, because we simple to all I would like to show, which is very useful in future implement or networks, etc. Photonics. So this is topic. This is not a related topic, what I'm showing you right now, and I hope. Just a minute, please. I don't know whether you are seeing the quantums or something different. So I will show you another step now. Photonic integrated circuits. So I hope some of Mrs. Are you seeing integrated circuits slide?
Yes, sir. It is visible, sir.
Yeah, I would describe the earlier paper that but now a little bit some easy material, so that it is not very complex for you to understand. I'll show you what are integrated circuits, how they be used. I already actually, the first part of the lecture, I've shown a lot of integrated circuits. Giving this, I should have done this earlier also. So I would like to show a few slides on these slides. This very photonic integrated circuits lecture, I would have just done with this without photonics. Okay, I would like to show you what are photonic integrated circuits. I have already described earlier, but once again, I'll show you some more pictures which will make you happy. You will understand. So integrated photonic circuits aims to create various components for a given system on a single substrate, either traditional or quantum. You can say, as I said, it can be analogous to integrated electronics, where you create a lot of electronic components on the same substrate. So there are a lot of examples are there of photonic integrated circuits. There are N by N switch arrays for networking applications. There is a chip for the sensor applications. 4G is a fiber optic gyroscope, which can be made on a chip that we made in our lab some time ago. Then recently people are talking about combining MEMS and optics. That's going to be an important development, including useful for other applications like quantum also. You can make the entire optical bench. You see, earlier in the previous ones, in the long, in the earlier previous lecture when I showed, there are certain systems that I showed which can be implemented on a bulk, on an optical table in a lab. So whatever you do it on an optical table in a lab can be converted onto a chip. This is called the micro-optical bench on silicon. That's an important development in the recent times that has happened. Just for those who are interested in photonic devices, integrated photonic devices, this is an example of an optical modulator. So for the time being, for some slides, you assume these are all traditional, not quantum devices, but they can be easily be converted into quantum devices, and we can find their operation, how they operate, etc., for single photons. Okay, so this is an example of an optical modulator. It is called a Mach-Zehnder interferometer. This entire setup, this is a top view. You can say that there's a box outside, which boundaries, it shows the boundaries. So you have light, you can inject light into this input port, and you can measure the light at the output port, and it is divided into two here and then combined back here, and there are two ports here. These are two electrodes, you can say, bluish ones are electrodes. You can put a voltage on top of this and then modulate. if you put a high data rate signal here, you can modulate it very high speed, say 10 Gbps or 100 Gbps. You can use it to modulate. This is called a lithium niobate modulator on a chip. So it has got a very good performance, a lot of bandwidth, low voltage of operation, chirping characteristics. All these things are there for this chip. This can be made in our lab in ISC here. For those who are interested, later on we'll discuss about photonic integrated circuits. So let me just a minute, please. I'll make it full screen. I will not describe all the slides, but only some important ones. This is another important device. I think we have seen earlier in previous slides. This is a directional coupler. There are two waveguides which are very, very close together. There are two input ports and two output ports. And if you launch light into first input port, you can exchange the light across the second port. And similarly, the light that is injected into this port can be got at the other port. So you can have a crossover state or bar state, depending on the voltage that you apply. Okay. So in the traditional sense, half the light, you can also plan to get half the light into this and half the light into this. Only thing is you have to choose the length to be half. So half the light can come into this and half the light can come into this. In the quantum sense, if you want to interpret this, so photon can come out of this port with a probability half and this port with probability half. And it can, once again, the first port can act as a Hadamard port 0 + 1 state superposition, and this one ket 0 minus ket 1. That is the interpretation of the directional coupler for quantum applications. Similarly, you can interpret the modulator also for quantum applications. Suppose you launch a single photon. At this point, it is a superposition state, and the ratios alpha and beta can be manipulated by using the photons voltage on these electrodes. So you can get a different superposition at the output. You can change the alpha and beta of the superposition at this, but the ket is same. The given state of the photon is remaining same, but the proportion can be changed. So these are all some of the features of photonic integrated circuits that people use. They are also based on single mode operation. You have alignment problems are solved. You can have good control of the light that is propagating in these devices. You can operate them with low voltages and short interaction lengths. They can be very fast. Electrode and capacitive effects are very less. Optical power density is very high, so you can have nonlinear optical effects, and you can create a single photon sources easily on the chip. And they are very compact, lightweight, and like VLSI, all the advantages you have. So historically, optical engineering has started in about 60s after the invention of the laser, and then a lot of fiber and these integrated optics has developed in 60s. Then, of course, as you know, in 70s you have a lot of optoelectronic devices. Then in 80s you have systems, fiber optic links have been laid all over the world, and many other applications started. And in the 90s, you know, it is the networking world, and so WDM, wave fixing, has become important in the corresponding components. So now people are talking about all optical elements, reducing electronics as much as possible so that you get the advantage of the bandwidth and all those things. So I'll show you a few devices which you find you have already seen in the previous lecture. I'll show you how they operate. And of course, why I'm showing you all this is if you want to implement some complicated function like the one that I'm showing on the paper, you need all these devices in their operation. You need to work out how they are how they behave by using mathematical techniques. You have to find out the equations of input-output relationship. All these devices that will be using complex system like the neural network system. So you can say that waveguide is a basic interconnection element, and you can also make a lot of passive waveguide devices like branches, tapers, etc. And you can have dynamic optical effects like electro-optic effect. Just now I have shown you electro-optic effect. You can apply voltage and change the properties of the waveguide. So essentially you will be changing the refractive index of the waveguide. So you know that if you change the refractive index, you can control the phase. You can make modulators, switches, etc. by using these techniques. So of course there are a lot of optoelectronic effects are there. There is interaction between light and matter, light and electrons, and so on and so forth. Finally, technology is going to be important. How you fabricate all these devices. So you can, for the time being, you can take it that we can fabricate these devices easily and in India. Of course, unless if you go to a more complex system like a neural network, then you will require more sophisticated technology. So these are all the different types of waveguides. These are all cross sections. You can have a buried waveguide. You can diffuse traces of impurities into the substrate and make a buried waveguide. You can create rich waveguides by coating another material on top of that and then etching out the unnecessary regions. Then you can put electrodes on top of the device and then you can make waveguides. That's a voltage induced. Loaded type means you can create another material on top of this. So these are all the cross sections of different types of waveguides which can carry light. So these are the technological issues. The different materials technologies that have come into practice, the most prominent being the silicon right now. Traditionally, glass has been important. They are very low cost devices. If you want to make, you can do it on glass. And crystals like lithium niobate has got nonlinear properties useful for generating single photon sources, etc. And magnetic materials can be used and all that. So depending on the material system, you can choose what are the fabrication techniques that you will use. Basically, you will require a lot of deposition techniques. Then if you are using semiconductors, you can use ion exchange processes, epitaxial growth techniques, and so on and so forth. So this is about how they are fabricated. For those who are interested, visit the site of our Nano Electronics Center. There is a Center for Nanoscience in Engineering in ISC. You can come and fabricate some simple ones there. For those who want to do PhD, etc., they want to go deeper, those who want to learn more into this photonics and technologies, etc., you can. Of course, we are willing to help you with the information. I mean, if you are, you can also get in touch with us to learn more about these details. Because we don't have so much time, I will just simply skip through some of this and I'll highlight one or two important points. The modes of the optical waveguides are important. That's what I said in the previous talk. Of course, for the modes, you have to solve the Maxwell's equations with corresponding boundary conditions and all those things. And you can create a lot of passive devices. Let us forget about mathematics for the time being. Passive, these are all the various passive devices that you will need in the neural networks and photonic devices applications. You have power dividers, you have polarizers, gratings I have shown already, lenses you can make. Generally, people call them as planar light wave circuits. So these are how the power dividers look like. There is one input port and two output ports, and light can be divided in principle. Conventional light can be divided across output ports. So you can divide them into 3 output ports, you can divide them into 4 output ports, you can cascade, and all that can be done. So these are directional coupler we have just come across. There are 2 waveguides very close to the light can tunnel across these, and you can also create a superposition state there. Similarly, you can have 3 waveguide coupler. So if you want to have a higher, of course, each of them can be, generally I said that these are single mode devices. You can also have more than one mode and then you can see what happens. And you can create higher dimensional operations by using these directional couplers. So star couplers are devices which will mix up the light in the mixing region and then they can redistribute across output ports. Suppose you want to create equal output at each of these ports, you can use such a mechanism. This is called transmission mode. Similarly, you can have a mixed region with a reflection mode of operation and so on. So polarization is an important problem in optics. You would like to create polarizers. You can send a TE, TM light through the input port and get only TE output, or you can change. You can rotate the polarization state. For this, you require what are called these anisotropic materials, like calcite, quartz, etc. Anisotropic materials. You make a conventional glass waveguide below this, and on top of that, you coat this anisotropic medium. So that's how we can make polarizers. So mux demuxes are necessary in communication applications. You can divide, if the input optical fiber carries 4 channels, lambda 1 to lambda 4, you can divide them across these output ports by using these gratings. Gratings are wavelength selective devices. The first wave grating will deflect the light to the first port, second grating will deflect the light to the second port, and so on. So you can separate out these wavelengths. And this is the reflection type of grating. So grating is what is used to manipulate. It can be used as a filter, you can say. So lenses, of course, also are important devices in optics. You can create lenses on the chip. So you can change the refractive index. You can have a graded the refractive index change or graded thickness also you can change, and you can get a lensing operation. You can use this lens for beam expansion or beam convergence. So gratings, we already mentioned that they have many uses. You can say we have used it for as a reflector earlier. You can also convert the modes from first mode to second mode, etc. You can convert by using a grating. Another important use of gratings is to couple light into the chip. We can couple light into the chip by using these gratings. So these are multi-purpose device that is used in communications and networking to as a mux demux or and so on. So there are several input ports and several output ports. You can get you can map light from any of the input ports to any of the output ports. So these two are mixing regions, and this is a delay waveguide region. The waveguides are of different length, so that there is a different relay across each of the waveguides. So when the light is incident at the output port, like one of the first port or third port, so it is a superposition of the light from each of these ports. So if you are using similar device for a quantum application, let us say the light is getting from this port, and it is a superposition of all the states. Of course, it's a fixed. In this particular case, the length is fixed, and so you cannot change much. But you can change the wavelength, and at each of the output ports, you have a different superposition. So that's how we can use these arrayed waveguide gratings in the quantum communication applications. So I'll show you a few devices where you can manipulate light in propagating in these optical waveguides. We have already seen that using electro-optic effect, that means changing the refractive index with the electric field, you can control the light, you can make a modulator, etc. Similarly, you can create a stress field, and it's called the acousto-optic effect. You can also create a magnetic field on the waveguide and have magneto-optic effect. You can also heat it. Thermo-optic effect is heating the waveguide and changing the properties. You can already have a lot of nonlinear optical effects can be used. So these are all the various effects to control the light propagating in optical waveguides. So they can be very effectively used in many applications. So this is an example of a thermo-optic device. You can have on-off switches based on this. Basically, it has got an interferometer on top of which you have two metal heaters. So you heat the waveguide and change the phase. So they are superposing at a different phase at the output. That's the main point in this. This is a very cost-effective device made on a glass with thin film titanium heaters and so on and so forth. So we have already seen a modulator that you can have two electrodes on top of this magnetic interferometer, and you can change the phase and you can put a frequency RF to these electrodes and get a high-speed modulation. So in the case of high-speed modulation, we have to think that these are not simply electrodes, but traveling wave electrodes. So you have to phase match and so on and so forth. Like in the microwaves, these will act as a microstrip lines. And so you can go for high-speed operation. So this can be made in lithium niobate with electrodes of titanium and so on and so forth. So this combines high-speed operations, microwaves and optics. So electro-optic switches can be made by manipulating the voltages on the switches, and you can get very different configurations. It's a very interesting thing for the quantum applications also. You can control how the qubits are represented, how they are manipulated, and so on and so forth. So acousto-optic effect is very, very important and useful in signal processing applications. You can filter out the signals, you can find the correlation between different input and output signals, and so on by creating gratings. See, this black patch is a grating created by this voltage. So you apply a high frequency RF, say 500 megahertz or gigahertz, and then you can create a very short, sharp, and quick traveling wave grating, you can say. The grating properties vanish once you remove the voltage. So you can deflect the light in different directions by using this acousto-optic effect. So you can look at this. For example, this is how you can create alternating plus and minus voltages are there here. And below that you have an optical waveguide, and the light propagating in this is affected by this grating. Some of the light can be reflected, some of it can be transmitted, and it's got its filter characteristics. In this example, I'm showing you TE mode is getting converted to TM mode. You can use a grating to convert the mode. That's what is the application of grating I have shown earlier. So magnetic fields can be used to manipulate the light propagating in optical devices. So particularly for polarization manipulation, you can use magneto-optic effects. But you will need magnetic materials. like garnets, yttrium, aluminum garnet, yttrium. These are the material systems that are used for magnetic optic devices. So nonlinear optics, I will not emphasize much. It's very important phenomena which is useful for creating single photon sources. And of course, traditionally you can use second harmonic generation is an important application. You can generate 420 nanometer light wave from an 840 nanometer light wave. Lithium niobate is one of the crystals which has got this nonlinear optical effect. It has got many properties, acoustic properties, electro-optic and nonlinear optical properties, etc. So one or two systems I will show you. Fiber optic communication system using this integrated optics, optical information processing system and a sensing system. So you can say that you can configure 5 electro-optic switches to make a 4x4 switch array. I have 5 switches here. Each can be put in a crossover state or bar state. 5 combinations, you can program it such that there are 4 input ports and 4 output ports. First, you can connect first one to the last one to the first one, and some combinations. Not all combinations are possible. You can make some interconnecting pattern by using this. Similarly, you can think of suppose in the beginning, I have shown you some operation of logic gate operations where you require 4x4 matrix. So you can use this similar example. You can program it. You can programmable logic gates you can create by using such electro-optic effect. Of course, that is a communication application that I'm showing you here, but you can easily think of logical gate operations. Similarly, optical processing can be done. It's processing of information signals by using optical means. This is simply imitating the traditional optical information system on a lab setup. So you have 2 lenses here, which can focus and defocus the light that is incoming. And what I'm trying to do here is using a grating, using this acousto-optic effect. I'm trying to manipulate the signal that is propagating in this. So the light can be incident. You can detect the light at any point on the output port, depending on the amount of spectral content of the signal that is creating this grating. You can have a spectrum of this at the output port. That is a typical information processing system. Of course, there are a lot of, this is a hybrid type of system where laser is outside. Similarly, this is one of the chips we made in our lab for sensor application. You have a gyroscope. Basically, what you have is you have a forward propagating light wave and a backward propagating light wave. And you can, when you combine this, is delta phi, phase shift between the forward and backward is proportional to the angular velocity of the object. Suppose you put this chip, this sensor on an aircraft or a missile, it can measure the rotation rate. The angular velocity is proportional to the phase shift, basically. So for this, you will require all these optical components like the power dividers, polarizer is there here. You have a phase modulator here, couplers, waveguides. All these things are there on a small chip. This is what we made in our lab in one of the projects for DRDO. So what I mean to say here is you can use a similar, of course, you have to have more sophistication, but you can also make a similar thing if you need to do something for a quantum communication or quantum computing system. So this is one thing that Japanese were very fond of. For disk pickup application, they have made integrated optical chip. So I have already shown you earlier that ring resonators are very important devices. People are using ring resonators for many applications in quantum communications and computing. So you can have simply rings of rings, and so on and so forth. You can do a lot of manipulation by using the ring resonators. This is one of the active areas of research in our lab. For traditional application, we have done many things, but we in the recent near future, we are planning to do similar things for the quantum communication applications by using the ring resonators. Similarly, I have talked about the photonic bandgap structures. These are periodic structures which have got either holes or airs embedded inside the silicon wafer. You can say that these are like a 2-dimensional or 3-dimensional gratings. You see, the first one is nothing but a normal grating. Light can pass through this and can get deflected and so on. All the grating applications that we discussed earlier. This is a parallel dielectric rods on top view on the silicon wafer. And this is a holes. You can create holes, hexagonal lattice of holes in the photonic. This can be used to manipulate light on a photonic chip. So that's the purpose I am showing you this. Of course, we have been working on this, so this is some of our work. So I'll show you one or two results. So we have made a 4-channel comb filter by using these photonic devices. So this is a bus waveguide, and these are the tap waveguides, and this is the spectrum of the light at the end of these detectors. You can see that each of these channels are well separated out. Similarly, we have made a 12-channel. One of the students has made a 12-channel comb filter, etc. So other important application that people talk about is the optical MEMS, very popular subject both from mechanical engineers as well as mechanical engineers as well as electronic engineers. You can combine optical devices also onto the same chip. That is an important outcome I can mention about optical MEMS. So people have made mirrors, etc., on the silicon wafer by using what is called this surface micromachining technology. MEMS technology can be used to make mirrors and all these things on a chip. These are somewhat bulky devices. We have already talked about waveguides, etc., on the chip, but you can make mechanically controlled devices. So these are all the optical MEMS devices that people have made on a silicon wafer. So mirrors they have made optical switches, variable optical attenuator. This is for a biomedical type of power application. These are all things that have happened in the optical devices world. So this is another example that we did in our lab on the sensor application. So you can create a pressure sensor by using MEMS. See, this interferometer you are already familiar. I'm controlling the phase of only this arm of the interferometer. This arm is not affected. So if there is a pressure on top of that, it will reflect in the output. So by calibrating the output against the pressure, you can make a MEMS pressure sensor. So that's all about the integrated optics. I'll go back to my slides, earlier slide, and then briefly describe what is that called? Just a minute, please. That paper on artificial neural network and relate to what I have shown some pictures earlier. So I would like to describe this paper a little bit more before we complete. Okay. So I hope you are able to see this paper again, Mrs.
Yes,
Bhavya.
sir. Yes, sir. It's clear, sir.
So this one of, you see, all these things that I have described earlier on photonic devices are useful. You see, this fellow Bhavani Shankar, he has finished his PhD, but much of it is theoretical. There's no implementation, fabrication, or anything that he has done. In future, we can do that. If someone is interested, you can try to implement this. Of course, a lot more theory needs to be done, mathematics of these photonics. But I will just give you a brief idea of what he has tried to do. I have already briefly mentioned, as you know, neural networks are very important in computer science and many applications, machine learning and artificial intelligence and so on. And you basically have very big architectures. So let me highlight on this is the architecture. Deep, you can say this is the photonic neural network. Simply neural, first of all, I think many of you are familiar with neural networks. So you can say that this is a neural network architecture. There are several waveguides or lines. All these blue lines can be considered when you implement as a waveguides. Okay. So there are several inputs and several outputs, and there are many intermediate stages. At each of the intermediate stage, you give a weightage. So light can be exchanged between these ports. So now you can imagine how it can be used. These entire several stages can be made on a small chip of lithium niobate or silicon or whatever you like. So this is how a typical neural network would look like. So when I zoom it, I suppose the zoomed pattern is appearing, is it not, Mrs. Bhavya? If I zoom here,
Sir?
if I zoom on my laptop,
Okay, sir.
it is zoomed in the
Yes,
presentation
sir.
of
Yes, sir.
the.
It is zooming, sir.
Yeah, that's good. So this is how a deep photonic neural network will look like. So I would like to now go to the equation. You see, of course, this is a weightage. The second picture will show you weighted cross connectors. You have input light, several input light signals, and then each of these S1, S2, S3 are one first layer of weightages first layer of inputs, and the weightages are there here. These are the outputs, C1, C2, Cn. So you can also implement, in fact, I would like to mention that if you have a micro mirror setup type of system, see, I'm talking about waveguides always, is it not? So you can also use the cross connect, mirror cross connects. People have made the N by N mirror cross connects. You can also use them as a weighted cross connector. So if you want to analyze the photonic layer, what do you have to do? You have to manipulate this equation. For the timing, you don't worry about what it is. This is called KL master equation. Kozlowski, he has chosen to represent or implement this equation. Okay, of course, in the literature, this is well studied, but no one has done photonics way of implementing. But you can solve this equation. You can solve this equation by using the photonic crystal lattice. So we will assume that you are trying to solve a complicated equation. And of course, you can represent in the operator notation in terms of, you can translate it into quantum terminology. See, this set of this equation, earlier equation is this, and now this equation is this with the density matrix 2. Let me reduce. So you can reduce it to this form in the quantum world. You will have to simply replace each of these differential operators, differential DL or differential operators, with quantum operators here. H is the quantum operator operating on the density matrix rho. So you can do a lot of manipulation using this. So you can analyze the topology of this. See, why you are calling deep photonic neutral network? There are several layers. That's the reason why you can call it as deep, that word deep. So how do you interact? How do you interpret this is an important question. This is a topology that you can think of. There are several layers. At each layer, there is a manipulator or weightage function, cross connects, and so on and so forth. You require several light sources here. The photodetectors are there necessary here. At intermediate stages, sometimes you will have to need the photodetectors. You have to simplify. And as you know, in neural networks, you have back propagation. How do you implement the back propagation is an important question. So actually, the light is propagating in the forward direction only. You see, from input to the outputs. But you can model this neural network as a back propagation model. You call it back propagation neural networks. So you can use light propagating in the reflected light, and actually light may not be reflected, but you can consider the weightages as being due to the reflections. That's how we can say you can use back propagation algorithm can be implemented on this. So after a certain amount of some more mathematics, he has converted this to quantum layers. A stack of quantum layers. This is how they will appear. This is the first layer. You can say with a deep photonic neural network with hardware, and then at a higher level, at a back propagation algorithmic layer, you have this can be called as a meta layer, and finally you will have an application layer. It's very easy to divide a complicated. It is very not exactly easy. It is very instructive or convenient to divide the problem into several layers before you can analyze. That's what he has done. He has divided deep photonic neural network layer, back propagation layer, and then the application layer. So I know that this is not a full description without describing each of these mathematical terms, but I hope some of you will be able to learn more about this. There are a lot of literature is there in the practice, and as I said earlier, people have not translated these into a implementable form. I can say that we can implement this using photonic devices that I have shown earlier. That's all about this particular paper that I would like to describe. So there are a few more students who have done PhD in our lab on algorithms or implementing some algorithms, like Google PageRank can be implemented using photonics, and also you can convert into you can convert that into quantum form, and search algorithms are there in the literature. You can try to implement search algorithms and so on, and many things can be done. Our lab is also very beginning in this subject, so I was able to show you a little bit. After we work more, we'll be able to tell you more about these things. And of course, tomorrow, one of my students, Mr. Rohit, will be able to talk about if you want to multi-level, or you can say quantum internet, he'll be able to tell you how it is being implemented and so on and so forth. We can say that photonics will be a good way to implement, but photonics also has to go a long way. You require a lot of devices like switches, modulators, mux, demuxes, and all those couplers, etc. has to be well developed. This is a very fertile area for those who want to do PhD in quantum computing and all these applications. I hope some of you will show interest. And I know that the organizers have told me that there are participants from different parts of India. And I hope some of you are already faculty in the college. So if someone is more interested, I can answer some questions. And then I hope, let me take some questions, then we'll discuss a little bit more because we have some more time. Okay. Before I conclude, I'll take some questions. So we have a lot of time for the questions. Please ask me. Whatever I can, I will answer. Yes, please.
Dear participants, if any queries, please you can raise.
I know there is a problem with the new topics, and also this online mode is not like a physical mode. You are not interacting directly with me. So that is the difficulty. Of course, you will have to study a lot before if you want to learn things. I would suggest for those who are interested, I hope many of you know about Nielsen and Chang's book. Someone must have highlighted earlier. Then there are several papers, a couple of papers I will send to the organizers. You can look at them. So let me see if there are some questions.
Dear participants, if any questions, please rise. Or if you can type in the chat box.
I think people have not understood fully. I know. I will send a couple of papers. I hope you will read, and you can, maybe if you are able to read today, you can ask Rohit tomorrow, or you can send me an email. So I will finally, I would like to thank you all for listening to me. And if you are more interested, you can see, I would say the subject is dealt with in IEEE Photonics Society. I hope some of you are members of IEEE. So this is the time when you are renewing your IEEE membership. You can join IEEE Photonics Society when you are renewing your membership. And also, as you know, there's a lot of photonics activity in India. And for those who are interested, you are most welcome to participate. There is what is called group called Prakash Bharati, which deals with applications of photonics. So for those who are interested in photonics and those who want to join photonics membership, etc., we can suggest what to do. Thank you very much.
So, dear participants, once again, if you have any queries, please you can ask.
Nowadays, you have too many seminars and less time to read and study. So I would say that you will definitely need to study yourself. Particularly this quantum is not at all acceptable on the face of it. See, that idea of a qubit, the idea of entanglement, the idea of decoherence, no cloning, and all these ideas are very, very strange from the common sense point of view. I would suggest you to reflect upon that. A single page or an equation, you have to look at it or ponder over it for several hours to understand. And of course, you will have to study quantum mechanics, quantum optics, and some of these subjects too. Of course, it's a well-established subject. It's not fictitious subject. People say that you will get a quantum computer by 2030, and most likely it will have a photonic chip. Okay, fine. Let us conclude at this. I will also thank organizers for calling me to this program, and thank you very much. Actually, I have come to Pulvendra once. one of my student was there in RGUKT. So I came along with him.
Okay, sir. The session was really very informative session, sir, on photonics and how the quantum will works on background, everything. So it is very informative session and it is very nice session, sir. Thank you, sir. Thank you so much for
Yeah, thank you very much.
accepting our invitation and delivering the session today. Thank you, sir. Thank you so much, sir.
Yeah, actually, I have a lot of material, but I have not made slides. Otherwise, we have some more work from our students. But of course, only if you have to go only systematically. Even though you have 1 week program, it is very difficult to learn in a short time. Okay, thank you.
Sir.
We'll conclude.
Okay, sir. Thank you,
Okay,
sir.
thank
Thank you
you.
so much, sir.